Okay, so we're here looking at the start of the probability unit, and we're going to start with discrete random variables. So you'll notice, actually, if I just go back, there are 4 parts to this criterion. So discrete random variables, binomial distribution, normal distribution, and populations and samples. So 4 distinct parts, and we're going to begin at the beginning. Discrete random variables. So if we just start by looking at a particular example that we have here with 3 balls drawn at random from a jar. So what we're saying is that there are 5 white and 7 black balls with replacement. And when you hear that term in probability, okay, this idea of replacement is the balls are put back once they're taken out and noted. Okay, the sample space, sample space, if you remember, is a list of all the possible outcomes. Okay, and so the sample space for this experiment is, you could have 3 whites, okay, where you go white, white, white. We could go black, then white and white. Okay, so at the moment these are all kind of written in order of the way they're drawn out. Okay, black first, then white, or white, then black, then white, 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 black, and so on. Okay, fairly evident with the way that's listed. Now, if we are interested in the number of white balls in the example, rather than the particular order with which they're drawn out, the sample space is going to become simpler and consists only of numbers. So if we let x, say, represent the number of white balls in the in the sample, then the possible values of x would be 0, meaning 0 white balls, or 1 white ball, 2 or 3 white balls. And since the actual value that x will take is the result of a random experiment, we say that x is a random variable. Okay, that's what we mean by this idea of random variables. Okay, now a random variable can be discrete or continuous, and in statistics and probability, discrete and continuous are referring to how the numbers come about. So in this example, x is a discrete random variable because the values that it can take on may be counted. Okay, discrete numbers are like counting numbers, and usually are like whole numbers, compared to continuous numbers or continuous random variables. They can take on a value in an interval, within an interval of the real number line, and so what that means is that they're typically generated from a measurement, say time or distance, mass, etc. In this particular example we're looking at, for the outcome of white, 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 that means x is equal to 3. For the outcome white, black, white, x is equal to 2, and so on. Now, with probability, associated with each event is a probability. Okay, so let's look at another situation. Okay, particularly we're looking at discrete probability distributions. We'll get into what that means in a second. A probability distribution for a discrete random variable consists of all the values that the random variable can take, together with its associated probability. For example, if x represents, in this case, the sum of 2 dice when they are rolled, we may represent the possible values and the probability that the sum is obtained in the table that we can see here. So what the notation that we've got here, PR, meaning the probability, that our random variable x equals some value which we're noting as this lowercase x. Okay, so basically we're saying what's the probability that our random variable x is equal to 2 or 3 or 4 and so on. So first of all, the probability that x, remembering that x is representing the sum of two dice. Okay, what's the probability that the sum of the two dice is 2? Okay, well, that's going to be 1 out of 36. There are 36 possible outcomes. Okay, and the only possible outcome is a 1 and a 1, rolling for the two dice to give us the sum of 2, and so it's 1 out of 36. For 3, a sum of 3, well, we can have a 1 then a 2, or we could have a 2 then a 1, so that's 2 possible outcomes out of 36. And so on it goes, and 7 being the most likely outcome. Okay, so we're going to come across these sort of ideas of probability distributions, and so this is an example of what one of those is. All discrete probability distributions must obey the following rules, okay, which, as you'll see, are fairly logical with your understanding of probability so far. Each probability must lie within this restricted interval. Okay, PR of x equals x, so this is basically representing our probability of the event occurring, must be between 0 and 1 inclusive. You can't have a probability that's less than 0, neither can you have a probability that's greater than 1. Okay, so that's fairly logical. Secondly, the probabilities of a particular experiment sum to 1. In other words, they add up to 1. So in maths, this Greek letter sigma means the sum of. Okay, so the sum of, let's write that there. Okay, the sum of all the probabilities of this particular event must add up to 1. So if we would just look at this particular example, if we added up all of those probabilities, because they are all the possibilities, okay, there's no other possible outcome that we could have. It's either adding to 2 or 3 or 4 or 5, etc., up to 12. Okay, and so with their respective probabilities, add them all up, it has to equal 1. Basically saying one of these outcomes has to happen. Okay, so that's that. And then so with that in mind, let's look over the page at first example. What we're wanting to do is find the value of k, okay, this unknown probability in this case, for the following probability distribution. Fairly straightforward idea. Going back to what we saw before, we know that all of the probabilities within this distribution must add up to 1, and so we could say that since the sum of the probabilities equals 1, 0.2 plus k plus 0.2 plus 0.3 plus 0.1 must equal 1. And so then we can easily solve for k. So we've got 0.2 plus 0.8 is 0.4, 0.7, 0.8. So k plus 0.8 equals 1. So k must equal 0.2. Okay, next example. Okay, so we're going to let x be the number of heads showing when a fair coin is tossed 3 times. Yes, I've just realised that that actually is not the third example. It's the second example. Never mind. All right, so we're wanting to find the probability distribution of x. Okay, so we've got a single coin tossed 3 times. So let's think about what the probability distribution will be. So if we draw up a table, and we've got x, here we have the probability that x equals that variable x. Now, how many heads can we get if we toss it 3 times? Well, it could come up 0 times, it could come up once, it could come up twice, or it could come up 3 times. So what is the probability that a head is going to show when the coin is tossed 3 times? I mean, if you're not sure, we can always do a tree diagram. So if you remember, we've got heads, tails, that's the first toss, second toss, same again, and then third toss of the coin, is that. So in 3 tosses, we can see if we add up down here, we've got 1, 2, 3, 4, 8 outcomes. Here is our sample space. Oops. And so here we're looking for the probability of no heads, and that's referring to this outcome here, which is 1 out of 8. 1 head is going to be this one here, or this one here. So that's 3 out of 8. 2 heads would be like 1 tail, and so that's also going to be 3 out of 8, which we can see, or 3 heads, which is that one there, 1 out of 8. Okay, so there's our probability distribution of our random variable x. That's part A. Part B, find the probability that 1 or more heads show. So 1 head here, or more, so it could be 1, 2, or 3. So the probability that x is greater than or equal to 1, okay, 1 or more. So we could add those 3 up together, or we could think, well, there's only one other, and all of these are going to add up to 1, so we could also think of that as 1 minus the probability that x is equal to 0, which is going to be 1 minus 1/8, which is 7/8. And then the last question here, find the probability that more than 1 head shows. Well, that's going to be the 2 or 3, and we can see from that it's going to be, so the probability that x is greater than 1, you could equally say that is greater than or equal to 2 even. Okay, so the way you write it doesn't really matter as long as it's correct. And so we can see from that it's just going to be half. Example 3. So we're looking at the random variable x here, representing the number of chocolate chips in a certain brand of biscuit, and is known to have the following probability distribution. So the number of chocolate chips range from 2 through to 7, and we're going to see here the most likely is 4. Okay, so what we're wanting to do then is, first of all, find the probability that x is greater than or equal to 4, which means at least 4 chocolate chips in the biscuit. Okay, what's the probability that a biscuit, say chosen at random, will have at least 4 chocolate chips? And so we can see we can either add all these 4 up, or we can add these up and subtract it from 1. That really doesn't make much difference in this case. So we'll just add them, 0.4 plus 0.3 plus 0.02 plus 0.02, which will be 0.74 as the probability. Excuse me. Okay, let's look at this one here. So we're going to think, well, what the heck does that mean? Alright, so cast your mind back. This notation here with that vertical line means given that. Alright, so we're looking to find what's the probability that there are at least 4 chocolate chips in a randomly selected biscuit, given that they're greater than 2. Okay, so what's happening here is that the sample space is being restricted to basically from 3 to 7. Okay, now we can use this rule. The probability that A given B occurs is equal to the probability of A and B divided by the probability of B. So that's the rule for conditional probability, which is not on your information sheet for methods 4. It is on the methods 3 information sheet, but not on the methods 4. Okay, so what does it mean when we apply it to this? So essentially that means what's the probability of here, I'm just going to put an equal sign there, so the probability that x is greater than or equal to 4 given that x is greater than 2 means we've got to find the probability that x is greater than 4 and x is greater than 2. Divide that by the probability that x is greater than 2. So first up then, what is the probability that x is greater than or equal to 4 and x is greater than 2? So what's the probability that both occur? Let's have a look at the numbers that we've got on here. Okay, so we're looking at this set of numbers because what's the probability that x is greater than or equal to 4 and it's greater than 2, which is from there. Well, the probability has to be that if it's greater than or equal to 4, it must be the sum of those. That's the that collection, or that sum of those probabilities will satisfy both of these conditions, both x being greater than or equal to 4 and greater than 2. Okay, so that's going to be what we've got here. Okay, 0.74. Divide that by the probability that x is greater than 2. X being greater than 2 will be 1 minus x equal to 2. So that's going to be 0.99, which should be the same as 74 over 99. I mean, you could give a decimal answer as well, but it will be rounded. And obviously it's very close to 0.75. We can just leave it as that fraction. Alright, the last one that we've got here, what's the probability that x is less than 5 given that it's greater than 2? So using our conditional probability formula, that is then the probability that x is less than 5 and x is greater than 2. Divide that by the probability that x is greater than 2. So what's the probability that x is less than 5 and greater than 2? Let's just go back up. Okay, that x is less than 5 and greater than 2 is going to be those two probabilities that we have there. That's the probability that it's less than 5 and greater than 2. So that's 0.65. Okay, so 0.65, divide that by probability that x is greater than 2, which is 0.99, and so we can see that's going to be 65 over 99. Okay, so for that part of what we're working through, then you can go on in the blue text, the Maths Quest text, exercise 10b. You can work through those. You're just doing similar questions to what we've just seen. Thanks for listening.